Somewhere in the Milky Way, right now, there may be a world not entirely unlike this one. A planet with liquid water on its surface. A planet with an atmosphere, with weather, with seasons. A planet where, over billions of years, chemistry became biology, biology became complexity, and complexity eventually produced something that could look up at its own night sky and wonder what lies beyond. Something that could build instruments and measure distances and ask the same questions we ask. And if that world exists, if that civilization is out there somewhere among the hundreds of billions of stars in this galaxy alone, they cannot reach us. Not because they are not intelligent enough, not because their technology is insufficient, but because the universe has built a cage around them, the same cage it has built around us. And a cage made not of bars and locks, but of physics, of energy, of time, and of distances so extreme that the word vast does not begin to contain them. This is not a story about whether aliens exist. The probability that some form of life exists somewhere else in a universe containing 2 trillion galaxies, each containing hundreds of billions of stars, each surrounded by planets, is so high that most scientists who have thought carefully about the numbers consider it close to certain. Life, in some form, is almost surely out there. The question that haunts physicists and cosmologists, the question that keeps them awake and arguing at conferences, is not whether life exists elsewhere, but why, if it does, we have never heard from it. Why no signal has arrived that we can unambiguously identify as the product of another mind. Why no ship has appeared in our sky. Why the galaxy, which by all probabilistic reasoning should be teeming with civilizations at various stages of development, presents to us a silence so complete and so strange that physicists have given that silence its own name. The Fermi paradox. Named for the Italian-American physicist Enrico Fermi, who in 1950, over lunch at Los Alamos National Laboratory, reportedly looked up from a conversation about recent UFO sightings and asked with characteristic directness, "Given the size and age of the universe, where is everybody?" It was a simple question. It remains, more than 70 years later, one of the most unsettling questions in all of science. And the answer that physics offers, the answer that emerges when you take the constraints of the universe seriously, almost when you sit with the numbers and let them speak, is both sobering and, in its own strange way, beautiful. The universe has built walls, and those walls are the laws of physics themselves. Let us begin with scale, because without a true sense of scale, nothing else in this story will land with the weight it deserves. We are not talking about distances that are merely large in the way a continent is large, or an ocean is large, or even in the way the solar system is large. We are talking about distances of a different category entirely, distances that require a different kind of number to express, a unit so large that it stretches the imagination past its comfortable limits. The Earth is roughly 12,700 kilometers in diameter. The distance from Earth to the Moon, which took Apollo astronauts about 3 days to cross, is about 384,000 kilometers. The distance from Earth to the Sun, a gap that light crosses in about 8 minutes, is approximately 150 million kilometers. These are numbers we have at least a passing relationship with. They appear in textbooks. They have been crossed by our spacecraft. They feel, if not exactly familiar, at least within the realm of the conceivable. Now step back further. The distance from the Sun to Neptune, the farthest planet in our solar system, is about 4.5 billion kilometers. Voyager 1, launched in 1977 and now the most distant human-made object ever built, has been traveling continuously for nearly 5 decades and has covered roughly 23 billion kilometers. It is, as of today, still within what astronomers consider the broad influence of our Sun, still within the outer boundary region of the solar system known as the heliosphere. And the nearest star? The nearest star to our Sun, Proxima Centauri, is approximately 40.2 trillion kilometers away. Not billions, trillions. More precisely, it is about 4.24 light-years distant, meaning light, moving at nearly 300,000 kilometers per second, takes 4 years and roughly 3 months to make that crossing. Voyager 1, at its current speed, would take about 73,000 years to reach it. And Voyager 1 is not even pointed in that direction. 73,000 years. Modern human civilization is roughly 10,000 years old. The oldest cave paintings are about 45,000 years old. And agriculture was invented about 12,000 years ago. Writing, the technology that allows knowledge to accumulate across generations, has existed for around 5,000 years. 73,000 years is longer than all of recorded human history, and then again several times over. And Proxima Centauri is the nearest star, the nearest one. Of the hundreds of billions of stars in the Milky Way, it is the one closest to us, and it is still essentially unreachable with any technology we currently possess or are likely to possess within any foreseeable time frame. This is the first wall, the wall of distance, and it does not stand alone. Yeah, because even if some civilization elsewhere in the galaxy wanted to send a spacecraft to Earth, even if they had studied our star and detected the faint chemical signatures of our atmosphere, and decided that this small blue world was worth investigating, they would immediately confront the second wall, which is perhaps the most absolute of all: the speed of light. In 1905, Albert Einstein published what became the special theory of relativity, and buried within its equations was a fact about the universe that no amount of technological ingenuity has ever managed to circumvent or even approach. Nothing with mass can travel at or beyond the speed of light, not because we have not tried hard enough, not because we lack the engineering skill, but because the structure of space-time itself forbids it with a mathematical completeness that has withstood every test for more than a century. As an object with mass accelerates toward the speed of light, the energy required to continue accelerating it increases without bound. The closer you get to c, the symbol physicists use for the speed of light, the more energy you need, not just more, but exponentially more, approaching infinity as your speed approaches. To push a single kilogram of mass to exactly the speed of light would require an infinite amount of energy. And the observable universe contains a finite amount of energy. The speed limit is not an engineering problem, it is a feature of reality. This means that any spacecraft carrying material objects, any ship made of matter, carrying matter, transporting matter from one star to another, can only travel at some fraction of the speed of light. Somewhat less than c, and even at, say, 90% of c, crossing from one star system to another takes years. To cross the Milky Way from one edge to the other, a distance of about 100,000 light-years, would take at minimum 100,000 years, even for light itself. For a spacecraft with mass, traveling at a large but sub-light fraction of c, it would take longer. Consider what this means for a civilization trying to reach Earth. Even a civilization located in a star system that is, by galactic standards, relatively close, say 1,000 light-years away, would face a journey of at minimum 1,000 years at the speed of light, and in practice several times that. The people who built the ship would be dead before the ship arrived at its destination. Every generation alive at departure would be dead centuries before arrival. The mission would span not lifetimes, but civilizations. This is where the engineering problems begin to compound into something that physicists describe, with increasing emphasis, as a wall. The rocket equation is one of physics' most unforgiving relationships. First derived in the early 20th century by Russian scientist Konstantin Tsiolkovsky, it describes a fundamental constraint on any vehicle that carries its own fuel. The ratio between the mass of the fuel and the mass of the payload increases exponentially with the desired velocity. The faster you want to go, the more fuel you need, and the more fuel you carry, the heavier your vehicle is. And the heavier your vehicle, the more fuel you need to accelerate it. The equation spirals upward without mercy. For a spacecraft to reach even 10% of the speed of light, 1/10 of c, which would get you to Proxima Centauri in about 42 years. Using the best propulsion concepts currently understood, the fuel requirements become staggering. With chemical rockets, the kind we use today to reach low Earth orbit, the calculation is not merely difficult, it is physically absurd. The fuel mass required to send even a small payload to the nearest star at 10% of c using chemical propulsion would exceed the mass of all observable matter in the universe. The numbers do not simply fail, they collapse into meaninglessness. Advanced propulsion changes the numbers: nuclear fission drives, nuclear fusion engines. DUS or antimatter propulsion, all of which remain either primitive or entirely theoretical, can improve fuel efficiency dramatically. The best physically conceivable propulsion system, one that converts matter directly to energy with perfect efficiency and uses it as thrust, is an antimatter drive. Antimatter reacts with regular matter in total annihilation, converting every gram of fuel to pure energy with an efficiency that no other process can match. In theory, an antimatter rocket could reach a significant fraction of the speed of light. In practice, there are problems that make antimatter propulsion almost science fiction in its current state. The largest particle accelerators humanity has ever built produce antimatter in quantities measurable in nanograms, billionths of a gram. As the energy required to produce even 1 gram of antimatter exceeds the total energy output of several nuclear power plants running for years. To fuel an interstellar mission, you would need kilograms or tons of antimatter. At current production rates and efficiencies, producing that quantity of antimatter would require more energy than humanity has generated in its entire history, multiplied many times over, and it would take millions of years to accumulate, even at optimistic projections of future production. Freeman Dyson, one of the most creative and rigorous physicists of the 20th century, studied interstellar travel with characteristic directness and concluded that chemical fuels are simply hopeless for the task. Though even the most generous assessments of advanced propulsion leave open the question of where the energy comes from, not the efficiency of converting energy to thrust, but the raw, enormous quantity of energy that must be available to begin with. One expert calculated that sending a single crewed mission to the nearest star within 40 years would require, for fuel alone, an amount of energy equivalent to several times the total current annual energy consumption of Earth. Not a small engineering challenge, a requirement that dwarfs any project humanity has ever undertaken by orders of magnitude. And this brings us to the third wall, the wall of energy. Energy is not evenly distributed across the universe. It is concentrated, in stars primarily, which are essentially sustained thermonuclear explosions held together by gravity, releasing the energy stored in hydrogen and other light elements over billions of years. A civilization that wanted to mount serious interstellar travel would need access to energy on stellar scales, not the output of power plants, the output of stars. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification system for civilizations based on their energy usage. A Type 1 civilization harnesses the total energy available on its home planet, all of the sunlight falling on its surface, the geothermal energy of its core, the energy of its winds and tides. A Type 2 civilization harnesses the total energy output of its parent star. A Type 3 civilization harnesses the energy of an entire galaxy. We are not yet a Type 1 civilization. Yet humanity currently uses a fraction of the energy falling on Earth from the Sun. On the Kardashev scale, we are approximately Type 0.73, advanced enough to have built civilization and technology, but nowhere near the energy mastery that interstellar travel would require. A civilization capable of serious interstellar travel would need to be at least Type 2, capable of capturing and directing the entire output of their star. This is not obviously impossible. The concept of a Dyson sphere, a structure built to enclose a star and capture its energy, has been discussed seriously by physicists since Freeman Dyson proposed it in 1960. But building such a structure would require resources and engineering sophistication that dwarf anything we can currently imagine. It would require dismantling planets for raw materials, processing them in zero gravity, assembling structures millions of kilometers in extent. It is, on any realistic assessment, a project of millions of years, not decades or centuries. And all of this energy would be needed just to get a spacecraft moving at a fraction of the speed of light. To then stop at a destination, because a spacecraft that cannot decelerate is not a spacecraft delivering a crew, it is a missile, requires the same energy investment again, applied in reverse. Accelerate to cruising speed, then decelerate to a stop. The fuel requirements, already staggering, roughly double. The rocket equation does not care about your intentions or your intelligence. It only cares about mass and velocity, and it is, as physicists like to say, merciless. But let us suppose for a moment that some civilization has solved all of these problems, that they have achieved Type 2 energy mastery, have built an antimatter drive, have constructed a spacecraft capable of traveling at 70 or 80% of the speed of light, and have pointed it in the direction of Earth. What happens then? The fourth wall appears, the wall of biology. the human body, and by extension, any biology that evolved on a planetary surface under the protection of a magnetic field in an atmosphere, was not designed for the interstellar medium. It was designed for a very specific and protected environment, an environment with particular levels of gravity, particular radiation exposure, particular atmospheric composition. Anywhere outside that environment, the body begins to fail. Not slowly and gracefully, but in specific, predictable, and in ultimately lethal ways. Cosmic radiation is the most immediate concern. The interstellar medium is not empty. It is permeated by high-energy particles, protons, helium nuclei, and heavier atomic nuclei traveling at significant fractions of the speed of light, the debris of supernova explosions and other energetic events. These cosmic rays pass through ordinary matter with ease, including spacecraft hulls and human tissue, and when they do, they cause damage. They ionize molecules they encounter, breaking chemical bonds, disrupting cellular structures, fragmenting DNA strands. On Earth, the planet's magnetic field and atmosphere deflect and absorb most of this radiation. In space, there is nothing to stop it. Astronauts aboard the International Space Station, still within Earth's protective magnetic field and spending months rather than years in space, accumulate radiation doses several times higher than those experienced on Earth. They return with measurable changes to their DNA, changes in their vision due to intracranial pressure alterations, losses of bone density, reductions in cardiovascular efficiency. The effects are manageable for short missions. For a journey spanning decades or centuries, they are not. The radiation environment in interstellar space is more intense than in low Earth orbit, and a spacecraft moving at a significant fraction of the speed of light would create a relative wind of interstellar particles that would increase the effective radiation flux further. Engineers have proposed various shielding strategies: water shields, magnetic deflection fields, exotic materials. Each solution adds mass, which loops back to the rocket equation. Each solution requires energy, which loops back to the energy problem. The walls are not independent. They reinforce each other. Beyond radiation, the physiological effects of long-duration microgravity are profound. The human musculoskeletal system relies on the constant stimulus of gravity to maintain bone density and muscle mass. In its absence, both deteriorate. Cardiovascular function changes in ways that are not yet fully understood. The immune system is disrupted. Psychological effects: isolation, confinement, the particular form of existential dread that comes from being separated from everything familiar by distances that light itself takes years to cross, are not negligible. There are proposals to address these biological challenges. Artificial gravity generated by rotating the spacecraft could mitigate the musculoskeletal effects. Shielding reduces radiation exposure. Psychological selection and training can prepare crews for extreme isolation. None of these solutions is impossible in principle, but each adds complexity, mass, and cost to an already daunting engineering challenge. And then there is the proposal that seems to sidestep biological constraints entirely: suspended animation. The idea of putting a crew into a form of long-term hibernation, reducing metabolic activity to near zero for the duration of a multi-decade or multi-century voyage, has been seriously discussed by researchers. Some animals, bears, ground squirrels, certain species of frogs, can survive periods of dramatically reduced metabolic activity. Human biology does not naturally permit this, and the proposed artificial versions involve challenges that have not been solved. Cryogenic freezing, the most extreme version of this idea, involves cooling the body to temperatures at which biological activity essentially stops. The problem is ice crystals. When water freezes, it forms crystals with sharp edges that puncture cell membranes. Freezing a living organism and thawing it without cellular destruction requires techniques that remain far beyond current biology. Some researchers propose replacing the water in cells with cryoprotectant chemicals that prevent crystal formation, a process called vitrification, which converts the tissue into a glassy solid rather than an icy one. While this approach works reasonably well for small biological samples and has been used in medical contexts for preserving eggs and embryos, whether it can be scaled to an entire human body without catastrophic cellular damage remains unknown. The biology is not obviously prohibitive, but it is unsolved. And this is the honest assessment. Biologically, the challenges of interstellar travel are serious, not fatal to the concept in principle, but serious enough that no realistic solution currently exists, and the solutions that are proposed each carry their own engineering costs that feed back into the energy and mass problems. Let us now consider the fifth wall, perhaps the strangest one, the wall of time. Even if a civilization launched a spacecraft tomorrow, a perfect spacecraft with perfect propulsion, it carrying a perfectly radiation-shielded and biologically sustained crew, the journey to a star system even a few hundred light-years away would take centuries, and centuries create problems that have nothing to do with engineering. What is the relationship between the civilization that launches a mission and the civilization that the mission was meant to represent after 300 years have elapsed? The world that designed and built and sent that ship would be unrecognizable by the time the ship arrived. The political systems that approved the mission, the scientific understanding that motivated it, the technologies that were considered advanced when it departed, all transformed beyond recognition or extinct. The crew, if they survived, it would arrive representing a civilization that no longer existed in the form it had when they left. Their knowledge base would be 3 centuries out of date. The communication delay, because radio signals also travel at the speed of light, and a ship 300 light-years from Earth means signals taking 300 years in each direction, would make any real-time guidance or support from home impossible. The crew would be utterly alone, in ways that no terrestrial explorer has ever been alone. Not merely physically isolated, but temporally orphaned. This is the time problem. Not time dilation, not the relativistic slowing of clocks, but the simple passage of time on the homeworld while an interstellar mission unfolds. A civilization that launches a mission is investing in a project whose benefits, if any, will accrue to a civilization that will be so different from the launcher that the original motivation may have ceased to exist entirely. History suggests that human projects rarely survive across centuries in their original intent. The Roman roads were maintained for centuries, but the empire that built them eventually dissolved. The medieval cathedral builders began constructions that took multiple generations to complete and succeeded, but only because the social structures supporting the project remained stable. Interstellar missions would require civilizational commitment across timescales that dwarf any previous human project, maintained through whatever disruptions, revolutions, extinctions, and rebirths a civilization experiences over hundreds or thousands of years. This is not merely unlikely. It may be for any civilization. Nearly impossible. And here the sixth wall begins to materialize. The wall that Robin Hanson, the economist and futurist, called the Great Filter, though it is less a wall than a gauntlet, a series of improbable transitions that any civilization must survive if it is ever to become capable of interstellar travel. The Drake equation, formulated in 1961 by astronomer Frank Drake as a framework for thinking about the number of communicating civilizations in the galaxy, includes a term whose value is perhaps the most uncertain of all: the average lifespan of a technological civilization. This variable is written as L in the equation, and it is the one that most dramatically shapes the final answer. If L is large, if technological civilizations routinely persist for millions of years, then even if civilizations are rare, the galaxy should contain many of them at any given time, and some of them should be old enough and advanced enough to have solved the engineering challenges of interstellar travel. If L is small, if technological civilizations reliably destroy themselves or simply go silent within a few centuries or millennia of reaching the technological level required to communicate across interstellar distances, then the galaxy may be largely silent not because civilizations never arise, but because they never last long enough to make contact. We have exactly one data point for L, ourselves. Human civilization has been producing electromagnetic signals detectable from space for about 100 years, since the widespread adoption of radio transmission in the early 20th century. We have been a technological civilization for longer than that. But in some definitions, but our electromagnetic leakage into space, the kind of signal SETI researchers listen for, is about a century old. We do not know if we will last another century, another 1,000 years, another million. Our track record is too short to permit confident extrapolation. What we do know, from that single data point, is that technological civilization is capable of rapidly developing weapon systems capable of ending it. Nuclear weapons exist. We came closer to using them than most people alive today are aware. The Cuban Missile Crisis in 1962 brought humanity to a genuine precipice, and it was resolved not through any masterly diplomacy, but partly through individual human decisions made under extraordinary pressure, decisions that could easily have gone differently. And we have also developed the capacity to alter the planetary systems that sustain our civilization through unplanned side effects of industrial activity, potentially destabilizing the climate that made our civilization possible in the first place. These are not abstract concerns. They are patterns of civilizational risk that, if they are common to all technological civilizations, would systematically reduce L and explain the silence of the universe. If civilizations reliably destroy themselves within a few hundred years of becoming capable of interstellar communication, then no civilization ever becomes old enough or stable enough to actually send ships across interstellar distances. The great filter, in this reading, is not behind us, it is ahead of us, and the silence we hear in the night sky may be its echo. A silence populated not by absence, but by endings. This is the most disturbing interpretation of the Fermi paradox. Not that we are alone, but that the galaxy is full of civilizations that never made it past the gauntlet that we are currently running. There are, of course, more optimistic readings. Perhaps the great filter is mostly behind us. Perhaps the development of life itself, the transition from chemistry to biology, from single cells to complex multicellular organisms, from simple organisms to intelligence, is so improbable that it occurs only rarely in the universe, and the silence we hear reflects not the destruction of civilizations, but their scarcity. Perhaps we are among the first, or among the few, rather than among the doomed. This interpretation is, while in its way, even more vertiginous than the pessimistic one. To be genuinely rare in the universe, to be an early experiment in a cosmos that is only beginning to develop the conditions for complex life, carries a weight of responsibility that the more familiar assumption of cosmic company does not. If we are rare, then we matter more. Not individually, not personally, but as a kind of phenomenon, as evidence that the universe can produce minds. If we are rare, then our survival is not merely important to us, but important to the project of awareness in a universe that spent most of its 13.8 billion years dark and silent. The astronomer and author Carl Sagan understood this with characteristic depth. He spent much of his professional life working on the question of extraterrestrial intelligence, as helping to design SETI protocols, contributing to the Voyager Golden Record, and writing with eloquence about the implications of either answer. The universe full of others, or the universe where we are essentially alone. He understood that the silence is not neutral. It tells us something, even if we are not yet certain what. But let us return to the physics, because there are two more walls worth examining, walls that apply not just to crude interstellar missions, but to any physical object, including the robotic probes that some have argued might be the realistic medium for interstellar contact, even if crude travel is impossible. The interstellar medium is not empty. Between the stars, space contains gas and dust, primarily hydrogen, at densities far lower than any vacuum we can create on Earth, but present. And a spacecraft moving at a significant fraction of the speed of light encounters these particles not as a gentle drift, but as a particle beam. At 10% of the speed of light, a hydrogen atom that the ship runs into carries kinetic energy comparable to a particle in a high-energy physics accelerator. At higher velocities, the energy increases rapidly. The leading surfaces of the spacecraft would be bombarded by what is effectively a constant stream of high-energy particle radiation, eroding materials, creating secondary radiation, degrading electronics and sensors over time. This is not an insurmountable problem in theory. Shields can be designed, sacrificial materials placed at the bow, the spacecraft shaped to minimize cross-section. But each solution adds mass and complexity, loops back to the rocket equation, and reduces the payload fraction available for useful scientific instruments or crew. At even higher fractions of the speed of light, the interstellar medium becomes genuinely dangerous in ways that are harder to engineer around. Dust grains, micron-scale particles that are distributed throughout interstellar space, carry enough kinetic energy relative to a fast-moving spacecraft to penetrate significant thicknesses of material. Some proposals involve laser-heated plasma shields or electromagnetic deflectors. Whether any of these can practically protect a spacecraft for the decades of travel required is an open engineering question without a clear answer. There is also the problem of communication. A spacecraft that has traveled light years from Earth cannot easily report its findings. Radio waves also travel at the speed of light. That's meaning that a ship 4 light years away takes 4 years to receive a message and 4 more years to reply. Real-time guidance is impossible. Any autonomous decision-making must be built into the ship's systems, operating without human input for years at a stretch. For crewed missions, this isolation is psychologically and practically devastating. For robotic probes, it requires artificial intelligence capable of making complex decisions independently. Decisions that may arise from situations the designers never anticipated, in an environment that has never been visited. And yet, it would be wrong to end here. It would be wrong to let the walls stand as the final word. Because the same universe that built these walls also built the minds that are now studying them, measuring them, arguing about them. The same physics that limits interstellar travel also powers the stars that sustain planetary systems, allows chemistry to produce biology, and permits the atoms in your body to organize themselves into something capable of reading these words and feeling something about the distances between stars. The walls are real. The physics is unforgiving. The energy requirements are staggering. The biological challenge is serious. The timescales humbling. The great filter genuinely alarming. No one who has sat with these numbers honestly has walked away thinking interstellar travel is easy or near. Most serious physicists who have studied the question carefully believe that if contact with another civilization ever occurs, yes, it is far more likely to be through electromagnetic signals, through radio or laser communication, than through physical visitation. A message can travel at the speed of light for free. A spacecraft cannot. This is, in fact, the operating assumption of SETI, the search for extraterrestrial intelligence, which has, since the 1960s, been scanning the sky for radio and optical signals that might carry the signature of another mind. The logic is straightforward. If the barriers to physical travel are as high as the physics suggests, then any civilization that wishes to make its presence known across interstellar distances would most likely do so not by sending ships, but by sending messages. Signals encoded in electromagnetic radiation, traveling at sea, requiring no fuel, no life support. No biological survival across centuries of transit, the most energy-efficient form of interstellar communication by an enormous margin. The silence we have heard so far, nearly 60 years of sky surveys with no confirmed signal, is itself data. It tells us either that communicating civilizations are rarer than optimistic versions of the Drake equation predict, or that they communicate in ways we are not yet listening for, or that the L term is small and civilizations go quiet quickly, or some combination of all three. The silence is not conclusive. It is not proof of cosmic solitude, but it is consistent with a universe in which the physics of travel and communication enforces a profound isolation on every island of intelligence. Think about what that means. If the physics is as constraining as it appears, and every experiment, every observation, every test of relativity and thermodynamics and the rocket equation has confirmed that it is, then the universe may be full of civilizations that are permanently, inescapably alone in exactly the way we are. Civilizations that look up at their night sky and count the stars and calculate the probabilities and build instruments and listen and hear nothing. Not because nothing is there, but because the distances are too great, the energy requirements too extreme, the timescales too long, the biological challenges too serious, and the civilizational durability required too rare for any of them to bridge the gap. Every civilization, in this picture, is an island, surrounded by an ocean so vast that no ship can cross it in less than thousands of years. Within each island, the full richness of mind and culture and curiosity and meaning. Between the islands, the void, not hostile, not indifferent in any personal sense, simply structured by physics in a way that makes bridges almost impossible. There is something both lonely and clarifying about this picture. Lonely because the company we might have imagined, the elder civilizations, the wise teachers from the stars, the confirmation that intelligence is not a cosmic accident but a recurring theme, may never come. Clarifying because it sharpens the question of what we do with the civilization we have here on this particular island in the time we have available. If the great filter is partly ahead of us, if we are at the precise moment in our civilizational development where the decisions we make about weapons, about the environment, about how we treat each other and our planet actually determine whether we survive long enough to become the kind of civilization that endures for millions of years. Then the silence of the universe is not just a scientific curiosity. It is a kind of warning, broadcast in the language of absence. Every star in the sky is a sun. Many of them have planets. Some of those planets may have life. A few of those life-bearing worlds may have produced intelligence, and of those intelligences, an unknown fraction may have reached exactly the point we are at now, capable enough to understand the universe, not yet certain they will survive their own capability. The fact that the sky is silent does not mean those worlds are empty. Yet it may mean that the transition we are living through, from a civilization that could destroy itself to one that has chosen not to, is the rarest and most critical transition in the story of intelligence in the universe. Not the development of fire or agriculture or writing or spaceflight, but the decision made collectively to continue, to not end it, to find a way through the walls we have built for ourselves rather than the walls the universe has built around us. We cannot blame the physics. The physics is simply what it is, consistent, ancient, uninterested in our ambitions or our fears. The rocket equation will not be amended. The speed of light will not be increased. The interstellar distances will not shrink. The biological fragility of living organisms will not be eliminated by wishing it away. These walls are permanent features of the cosmos, as fixed as the laws of thermodynamics and the value of fundamental constants. But none of those walls says we will not survive. None of them says the experiment of intelligence on this planet is fated to end before it has properly begun. They simply say that if we want to persist, if we want to be among the civilizations that endure long enough to become truly interstellar in ambition, even if not in practice, we need to survive the gauntlet of our own making first. The universe is old. It was old before the sun ignited. It will be old long after the sun dies. In all that time, on all those worlds, with all those possible minds, the silence suggests that what we are attempting, the construction of a durable, self-aware, curious, yet technologically capable civilization that chooses survival over destruction, may be among the hardest things the universe ever produces. Not harder than the physics of interstellar travel, but not easier either. Tonight, the stars are out. They are exactly as far away as they have always been. The nearest one is 4 light-years distant, and there is no ship that could reach it in a human lifetime, and there may never be. The galaxy is full of worlds we will never visit, suns we will never see up close, civilizations, if they exist, we will never meet. And yet here we are, small and warm and alive on a rocky planet, in a thin layer of air, looking up, asking the question, running the numbers, sitting with the silence and refusing to let it be the last word. That refusal, the refusal to accept the silence, is final. Now, the insistence on continuing to ask, continuing to listen, continuing to build and measure and wonder may be the most important thing we do. Not because it will collapse the distances, not because it will repeal the rocket equation, but because the universe spent nearly 14 billion years producing something that cares about the question. And caring about the question, in a universe this vast and this old and this largely silent, might be the rarest thing of all.